Somebody almost as famous as me, Freddy Cachazo from the famous VC lab neural relations. He will give us another approach to language.
That's right, that's right. So actually the perfect order is the other way around, because then you have ended up with the famous guy. That's okay. Well, that's true. So I decided to, well, thank you everybody for coming to a talk where you don't know the title or you didn't even an abstract. But Nima gave you more or less an abstract yesterday. So I decided to call this talk Trees. Okay, so Nima gave you yesterday, or in his 4 lectures, a way of thinking about amplitudes that is basically a little game where you put together building blocks. And these building blocks are very sharply defined. They basically look like tetrahedra. So you find triangulations of a given polytope, and then you compute the little volumes, and you put them together. But he also said yesterday that there is another approach. There is an approach where these building blocks are replaced by nice, smooth objects. Okay? So what I'm going to tell you today is work that I've done with some E and Ellis Yuan, a postdoc and a graduate student at Perimeter Institute, were really, really good. And yeah, these guys really pushed forward what I'm going to tell you today, so it's very important to give them lots of credit. And let me start the story by telling you what is it that we want to compute today, okay? So what we want to compute is something from which we can actually compute cross-sections. So we all learned in quantum field theory 1 that you can compute the differential cross-section of a given process where you have 2 particles coming in, say A and B, and some particles in the final state coming out, as the mod square of an object divided by 4 times the energies of the particles that are coming in, times the relative velocity, times the d-bits, or the Lorentz invariant phase space of the final particles. Okay? So this object here of AB going to the final states is the object we want to compute today. So this is going to be the main object of interest for today. So once I present it to you in the new way we're going to learn, you can just use it and plug it into this formula to compute any cross-section you want. Okay. In this definition, this object doesn't have any momentum conserving delta function because all that goes into the definition of the ellipse. Okay? Very good. As the title of the talk implies, we're only going to be working at 3 levels. Okay? So unlike the previous talks where Nima described a very, very good understanding of a formalism where you can describe amplitudes at all loop level, in this smooth approach, at this moment, we only understand the trees. Okay? But hopefully, some progress will be made and we will be able to understand more than trees. So let me start a little bit with history. So let's start in the 80s. And I think I have to start here because I asked Nima and he didn't start there. So I'll have to start in the 80s with Park and Taylor.
I didn't write down a single scattering.
You didn't write a single scattering. You didn't even write the momentum of Park. Well, that reminds me that, of course, when we studied quantum field theory, we learned about crossing. And at least at 3 level, we can use the LSC formula. At least at 3 level, it's easy to prove that amplitudes are crossing symmetric. And that's why we usually think about them as rational functions of momentum where all momenta are taken to be incoming. So we forget about which particles are incoming and outgoing, and we just declare that everybody's incoming or everybody's outgoing. That's why we can talk about scattering amplitude of n particles without distinguishing who is incoming and who is outgoing, because we can use the same rational function to describe all the other scattering or particular scattering amplitude by the analytical equation. Okay? So Park and Taylor in the 80s made a shocking discovery. They realized that the sum of many Feynman diagrams, actually they did it because they had to compute some scattering amplitudes of gluons. And gluons carry color. They computed amplitudes that had to be computed for practical purposes. And they realized that they had a very, very simple decomposition in terms of variables that are not the standard variables that you use. Okay? They are not the standard momentum and polarization vectors that you have to use to describe gluons. So in the standard description, you will give a momentum vector and a polarization vector to describe the states of a gluon. The momentum vector is a null vector. Okay? But Park and Taylor realized that if you use the top two components of Nima's Z's that he kept writing but never told you what they were. So Nima's Z's, he wrote this 4-component object, and the top two components of this object, let me call them lambda 1a and lambda 2a. These two things, never mind who they are. Okay? That's not important for our discussion, and the reason is that Park and Taylor found that a certain class of amplitudes can be written in terms of only these two objects. In fact, they can be written in terms of combinations of these two objects that are given like this. Okay? So this is a definition. And in terms of these building blocks, they found a very beautiful formula for the scattering of particles. Gluons carry helicity. They are massless particles, so they come with two possible helicities, plus and minus. So they found, Park and Taylor, in our description where all particles are coming, that if you have two particles of negative helicity and any number of particles of plus helicity, the formula for this amplitude is incredibly simple and is given as follows. So the two particles of negative helicity, let me call them I and j. So the only dependence on them comes here in a factor of this form, but with I and j to the fourth. And there is here a sum over permutations of n minus 2 elements. And this is a formula that Nima should have started his talks, but he didn't. Sorry. Let me go up to here. N minus 2, n minus 1. I said n minus 2, so I should actually add the other 2. So I can go to n minus 1, and n1. And here, in the numerator, there is a little factor that I'm going to draw like this, which is 1, omega 2, omega 3, and so on, up to omega n minus 1 and n. Okay? So what is this numerator? Well, I told you that gluons carry color, right? So we need some color structure somewhere. And gluons, here I'm going to think about generalized gluons, actually transforming in the Young representation of UN. And in order to define this for you, all I have to do is to tell you that whenever you see a trivalent object here, what I mean by this is that if the corresponding lines have some color index A1, A2, and A3, this means a structure constant of the gauge group of the form A2 and A3. And if you see that two lines, that a single line is internal, it means that you're supposed to sum over that index. Okay? So you just solve together structured constants according to that little tree that I showed you there, and sum over the color index that appears in internal lines. And then you just get that string, you put it in the numerator, and thus the Barth-Taylor formula for any number of particles.
Okay, so we still know what CA is, because you haven't told us what lambda 8 is. Please tell us.
Yeah, I thought I could get away with not telling you what lambda 8 is. That's good.
I know something is.
Yeah, this is. Okay. Okay. Since you want to know, so take any vector construct it with the Pauli matrices. Okay. Construct a 2 by 2 matrix. So let me call it, let me just drop the index A because it's too much to write. Okay. The determinant of this matrix happen to be just the norm of the vector. And if we have a massless vector, this is 0, right? So if you have a determinant, a 2 by 2 matrix that has rank 1, it means that the rows are proportional to, the 2 rows are proportional, or the 2 columns and the 2 columns are proportional. So that means that I can write this as something that looks like, so let me write it as follows. So the constant of proportionality, so I'm going to write, say, a vector here. Okay. And I'm going to allow any proportionality constant here and any proportionality constant here, so that I construct the most general matrix of rank 1. And the constant of proportionality here I'm going to call lambda 1, and the constant of proportionality here I'm going to call lambda 2. So this is the most general 2 by 2 matrix that has rank 1. Now that means that any massless vector defines a 2 by 2 matrix that can be written as follows. Where these indices are these indices that I've written. Okay? Now it turns out that miraculously, that particular amplitude only depends on the lambdas and not on the lambda tildes. Now, what do you think are the last 2 components of Nima's Z? No, they are not. They are linear combinations of the lambda tildes together with the lambdas in a very smart way that was designed or was invented by Andrew Hodges. So, but that will not enter in our story. Okay? So let's continue a little bit with the history.
So the intermediate states here are only gluons, or is there?
The external states here are only groups.
Well, the internal is tree level, so
It's
only
3 levels, so only the internal states are only groups. Okay, so in the late 80s or early 90s, I don't quite remember now, Nair made a very interesting observation. He figured out that first, this object, the object that appears in the permutation, which I didn't tell you, but that object is permutation invariant, even though I wrote it in this way where I single out particles 1 and n to be special. You can check that this object is permutation invariant by using Jacobi identities. Okay? And simple properties of these 2 by 2 determinants. These brackets are just determinants of these little 2 vectors. Okay? So you can show that this is actually permutation invariant. And what Nair realized was that this object actually looked like correlation functions of currents living on a cyclic one, on a 2-sphere. So from that point of view, let me actually define these things. So if I have a cyclic one, a sphere, let me distinguish endpoints on the sphere, and I'm going to denote them by sigma. So there are endpoints on the sphere, and I'm going to call them sigma 1, sigma 2, all the way to sigma n. And I realize that these objects are basically objects that you can get by studying some correlation functions on the sphere. So let me call this Cn, okay? And it's a permutation invariant object. Now, he didn't know what the sphere was, where did it live, and what purpose in life it had. For that, we had to wait until 2003. So in 2003, Witten found a nice interpretation for that sphere. And he interpreted the sphere as a wall sheet of a string theory, okay? But not a regular string theory, because it's a string theory whose target space was somehow a strange space, was a twistor space. The twistor space of Penrose, which he told us, Penrose told us how to go back and forth between space-time, four-dimensional space-time, and twistor space. Okay? So we can realize that if you think about this sphere as the wall sheet of a string theory, and just by the standard rules of a string theory, you map it into a target space, so this sphere will go into a target space. You will get an object here that can then be translated into the correct scattering amplitude. And he realized that the fact that there are different helicity sectors has to do with the fact that there are many different possibilities for mapping CP1s into twistor space, classified by a number. That number is called the degree of the map. That degree, he matched to the number of negative helicity gluons present in the scattering amplitude. He realized that the degree had to be the number of negative helicity particles minus 1. So the case of Park and Taylor was obtained by using a map of degree 1 from CP1 to twistor space. A map of degree 1 is basically a simple embedding of the same object into the space. That's why the CP1 ended up being a CP1 here, a boring one. And when mapped into space-time, you got something that looks like what Park and Taylor had. But now you could generalize it for any number of negative helicity particles, something that people were looking for, but nobody could generalize this to something nicer. Okay? Very well. So this is a story. Now, you could say, well, twistor space is something that depends on the fact that you're working in 4 dimensions. I mean, that was the one thing that Penrose stressed, that there is something very nice about 4-dimensional space-time, where you can define this space, twistor space, that has very nice properties. So, from this picture, you would say, well, generalizing this to higher dimensions might be impossible, because everything seems to depend on twistor space. Okay?
Freddy?
Yes.
So what's the theory on CP1? So is some field theory that different CP1?
Yeah, the theory, this is just a regular string theory that has it's a very simple string theory that has very few fields. You have to, that is very constrained by the standard arguments of the string theory.
But Mayer didn't even know what string theory is. The procurement was just...
No, he simply said that you have fermions, yeah, so if you have 2 fermions on the sphere, the OP is 1 over the separation, which is what this looks like if you write it in inhomogeneous coordinates. That's right. Very good. So, how do we do this in higher dimensions? I mean, and not only that, for this string theory to live nicely in twistor space, you need 4 supersymmetries. So you could say, well, you want to do something that that lives in any number of dimensions, and if you do, clearly you have to give up supersymmetry, because in 13 dimensions you don't have supersymmetry. Not only that, you have to give up these beautiful variables, the lambdas and the lambda tildes, right? Because you don't have sigma matrices, you will have to work with gamma matrices. And to impose that you have a massless vector, you have to impose something that are called pure spinor constraints, something very complicated and that depends on every dimension. So if you want a formula that is valid in any dimensions, you really have to go back and work with these guys. There is no other way. Okay? So, what of this picture we want to keep and how much of this can be generalized? So, well, if you don't know anything, I mean, if there are no clues, at least you should keep the things that look nice, right? So that would be a good approach, just aesthetic approach. So, more generalizing. So the proposal is the following. I want to keep the CP1. That looks nice. Okay. I want to find a description for the scattering of massless particles that relies on a CP1. We don't have time, but I could motivate why this is nice. Why it's much better to think about the modular space of points on a sphere rather than thinking about the space of kinematic invariants. Just a space of Lorentz invariants made out of massless vectors is a space that has dimension n times n minus 3 over 2. But that space is a space that doesn't know any physics. But the space of the modular space of genus 0 Riemann surfaces with n punctures is something that knows a lot of physics. So that's why we decided to keep it. Okay? Very good. So like in the movies, please turn off your phones and enjoy the show. Okay, so I want to keep this. Now, what do we use to replace twistor space? Now we want something in any number of dimensions. Well, the proposal is that what you do is to find maps from the sphere into momentum space. Okay? But not only into momentum space, we want massless particles. So I want to map the sphere into the non-con in momentum space. So I want to find a map from the sphere. Imagine that I call a coordinate on the sphere z, an inhomogeneous coordinate on the sphere, and I call it z. So I take a map, a collection of polynomials of some degree. I haven't told you what the degree is. How many of them? Well, I take d of them, if I'm in d dimensions. And I map the whole sphere. I want the whole sphere to be mapped onto the line cone. Okay, so it's gonna be pasted on the line cone. Okay, so if I do that, maybe I have a chance of generalizing all these formulas. So a natural thing to do would be to identify the momenta of the external particles. Okay? So here I want to change, since we're going to go to any number of dimensions, and that was in 4 dimensions, to actually make the distinction, I'm going to call the external momenta by k. Okay, so we have a set of m momenta in d dimensions. They are all known, and they satisfy momentum conservation. Okay? So a natural conjecture would be to say that you want the Ka's, the momentum of the particle A that lives somewhere here, to be related by the image, just to be the image of the map. That would be nice, right? The problem is that if you do that, of course, imposing the constraint that the whole sphere is mapped onto the non-con implies this condition. But momentum conservation will not work. Okay? So this approach would be too late. How can we fix it? So this doesn't work. Well, the way to fix it is the following. Let me just tell you how to fix it. And that will also teach us the degree of P. Here is a proposal. So you define this differential form, a one form, made out of the map. It's a polynomial of some degree, okay? And this differential form is supposed to live on the space, on that Riemann surface that has punctures. But how do you know that a Riemann surface has punctures? Well, the forms that you define must have poles on the punctures. So here are all of them, okay? Of course, if this vector is null, when I compute the residue, I basically get this answer. Except that I also get a product over sigma A minus sigma B for B different from A. So this factor doesn't change the fact that this is null, right? Because it's an overall factor. So when we compute P squared, we get 0. That's still keeping the good thing about this. Now, from this formula here, it's not obvious that momentum conservation is satisfied. In fact, for a genetic polynomial, it will not be satisfied. But what if I choose the degree of the polynomial to be n minus 2, the number of particles minus 2. So choose the degree of each of these polynomials to be exactly n minus 2. Well, you see what happens. If I use this formula here, I get a sum of this differential form, sum over all these poles. But all these poles are all these poles here. So I can now use a contour deformation argument and enclose, so combine all these contours into a single one and deform the contour to pick up just whatever there is at infinity. But if the degree is n minus 2, you see that the degree of the denominator is n. So if the degree is n minus 2, there is no pole at infinity, and I get 0. So momentum conservation is a residue of the order. Right? So this condition is true just by the fact that I chose the degree to be n minus 2. I'm sure you're all thinking, but perhaps to be polite, you're not asking why n minus 2 and not something smaller. Something smaller would also work, right? Something higher clearly doesn't work. And the reason is that if you count the number of parameters, you actually have to saturate the maximum degree or the inequality of the degrees in order to be able to match the two spaces, the space of kinematic invariance and the space of maps from the Riemann surface to the non-counting momentum space. Okay? So quite nicely, it fits perfectly. Now, the other good thing is that in higher dimensions, more than 4, there is no helicity, right? Massless particles are not classified by helicity, right? The little group is very different in higher dimensions. In fact, it depends very strongly on dimensions. So we didn't want to have something that depends on the degree. We wanted a fixed degree, okay? And indeed, we find that it's fixed. And that's the end, okay? Now, we have to solve these equations, okay? These are equations for what? Well, I told you that this is a polynomial. Maybe I should have written it down. Of degree n minus 2. So we are supposed to find the constraints on the coefficients of the map. These are the coefficients of the map. So that these equations are satisfied, and not only that, but p squared of z is equal to 0 for any z, okay? But if you just sit down and try to solve this, good luck with that. It's very complicated. You could try, but you have to suffer a little bit. But let me show you a simpler way, not of solving the problem, but giving you a different formulation of the same problem. And it's the following. Let me start by solving these equations first. Okay? And only after I solve these equations, I will tell you, I will impose a condition that this is not. So how do I solve those equations? So the first step is that all I have to do is very easy. I just have to declare, or the solution to those equations is nothing but the sum from B1 to n of Ka mu, Kt mu, divided by C minus sigma B. As everybody agrees, this is a solution of that problem, right? Now you just combine this into a single, you put it in Mathematica, you say it together. And Mathematica, and then you do numerator. And Mathematica will give you what P is. Okay? That's very good. But now we have to impose that this is a null vector. Okay? So the second step is to impose that this is a null vector. So we have to dot this with itself. And we have to require this to be 0 for any z. But this has to be 0 for any value of z, means that, well, this is a rational function. It seems to have poles. First of all, it vanishes at infinity, trivially, right? Because it only has one more z's. So if we manage to prove that the residue at each of the poles is 0, then the function must be 0. Okay? So all we have to do is to show that the residue at each pole is 0. But the location of the poles is nothing but the location of the punctures. So I have to compute the residue at z equals to c. And impose that such a thing is 0. Well, what is the residue at z equals to ca? Well, that's very easy to see from here. I'm summing over b from 1 to n and c from 1 to n. So if you compute the residue, that residue is nothing but the sum over, let me call it b again, from 1 to n, but not including a, of Ka dot Kb divided by sigma a minus sigma b. And I have to impose that this is equal to 0 for all a. Okay? So those are the equations that link the location of the punctures to the kinematic invariants Ka dot Kb. Those kinematic invariants are.
So terminology, what is puncture?
Sorry?
Terminology, puncture, what is it?
The puncture locations, yeah, so I'm thinking about CP1 with endpoints removed.
Oh,
The points that you remove, people like to call them punctures. So as if you really punch the points on the little holes on a balloon without popping. But it's so really they think about them as being little holes that you remove from the sphere. So when I say puncture, I refer to those locations. Now, when we found these equations, we were very excited because they look like universal equations that have to be satisfied whenever you have the scattering of massless particles. I haven't told you if I'm doing gluons, gravitons, scalars, I haven't told you anything, right? So somehow we were convinced that these objects, these equations were fundamental. One reason to be convinced about that is that when you tune the external momenta to do funny things, like going to a factorization channel, these equations immediately imply that the punctures behave also in a funny way. So when you separate particles, you use a factorization channel where some set of particles, their momenta, the sum of the momenta of a group of particles becomes some shell. Somehow the punctures split into two groups, just through these equations. So we decided to call this the scattering equations. It was a little bit bold because we didn't know if we could ever reproduce any scattering amplitude from the equations, but it was too good to resist the temptation. So we call these scattering equations, and we conjecture that there must be a way of writing the amplitude, this m I was telling you about, for any theory of massless particles as an integral over the location of all the punctures, okay, on the sphere, of an integral that depends on the external data, depends on the wave functions of the particles. If they are gluons, they will be polarization vectors. If they are gravitons, they will be polarization tensors. The punctures, of course. And this integral will be constrained to satisfy the scattering equations. So let me call this C, because I like the A first. Okay? So this was a conjecture. Sadly, this equation doesn't make any sense for two reasons. The first one, well, actually three. The first one is that we had no clue what these items. That's for one thing, but it didn't mean that it didn't make sense. The problem for which it didn't make sense is that this object is ill-defined, because n minus 3 of the, only n minus 3 of the n equations are linearly independent. So if you impose the support of n minus 3 of them, the other 3 become 0 immediately. So you get 3 delta functions that are 0. So that's terrible. Okay? So we have to find a way of fixing that problem. So the way to fix that problem whenever you have something like that is actually very easy. What you do is that you do this and you put a prime. And you tell people, well, this is on the support of those things, whatever it can be. Now, we wanted to describe theories that are physical. So if they are physical, they must be permutation invariant in the labels. Okay? Even for gluons, if you keep track of the color structure, it must be permutation invariant, despite what many people will tell you. And the reason is that they are stripping out the color structure and they are only looking at a given structure. But if you keep everything, they must be permutation invariant. So we had to find a permutation invariant way of imposing this support. And the answer turns out to be very simple. So let me introduce a notation here, because we don't have too much time. So I'll just simplify my life by telling you that a sigma with two labels is nothing but the difference of the sigmas. Okay? This is just notation. So, to write something that is permutation invariant in the labels, all I have to do is to impose the constraint over n minus 3 of these objects. So I'm going to say, well, I'm going to impose a constraint over A different from I, J, and K. So I just remove 3, any 3, and I impose these equations. Okay? Now, if you change your mind about what I, J, and K was, when you try to put it here and you try to compare the two equations, you pick up Jacobians. And you realize that if you put here this object, this doesn't depend on the choice you make. Okay? So this is my definition of the product prime of this. Okay? It's permutation invariant. Now, if we really take seriously that we're working on CP1 and not on S2, there is a very important difference between S2 and CP1. Okay? I'm giving you time to think what the difference is, if you're wondering where it is. The difference is that CP1 is an S2 with a complex structure. Okay? Now, if you have a complex structure, and you integrate over the model space, you have to mod out by complex coordinates that you put in that give you the same complex structure. Okay? And that group for the sphere is an SL2C group. It means that really, out of my n locations of the punctures, I shouldn't integrate over all of them, because I can use SL2C as a group acting on the sigmas to fix any three of them. The action on the coordinate z is AC plus D, CC plus D, where AB minus BC is equal to 1. So I can fix any three of them to be anywhere I like, okay? So I shouldn't integrate over all of them. So since we're physicists, I can say that this is a gauge redundancy, and I divide by the volume of the group. Never mind that it's infinity. It's good because the integration region that I'm overshooting is also infinite. Okay? Well, but if you want to compute anything, we really have to know how to deal with this. Well, but we all know we use Fayette-Popov to fix the redundancy, and in the end, you can integrate. You can use the SL2C to fix any three. So let me choose to fix any three different from P, Q, and R, D sigma D. Okay? Well, D is not a good choice for notation, but it's actually a terrible choice. So let me put an E. And the Fayette-Popov determinant that you get is sigma PQ, sigma QR, sigma RP. Isn't that amazing? It's exactly the same that appeared on the other side. So maybe there is something to it. Okay. Very good. So at least we can make sense of this formula now. This is a formula that makes sense. And we can compute this with it if we only knew what this object was. So let's think about gravity first. Okay? So what could that object be? Well, it has to be something that is gauge invariant. So if we replace any of the polarization vectors, in the case of gluons by just a momentum vector, we should get 0, right? That's one constraint, gauge invariance. But there are tons of other constraints, right? Something like when you have massless particles, you can impose, you know very well what any amplitude has to do when you take one of the particles to be soft. Okay? Just by putting those two things together, you sit down, you try 10,000 things until one of them works. Okay? That's the approach to solve a problem like this. So you do it, and you come out with the idea that you have to define a matrix that I'm going to call psi. Okay? And this matrix psi is going to be constructed out of the data that I have. So this is the matrix. So it's just going to take me a little bit to write down the matrix. But once I write down the matrix, we will be done. So I want. Oh, this is terrible because it's supposed to be 4 blocks, and they are all supposed to have the same size. So I'm going to be in trouble there. So I better move my matrix here. Now I have space. Sorry. This is actually. Maybe there is no problem. Oh. So let me write this. K1 of K2, sigma 1, 2. K1 of Kn, sigma 1, n. Now you put this line and this line here. And right here, K2 of K1, sigma 2, 1, 0. K3 of K1, sigma 3, 1. Kn of K1, sigma M1, all the way here to 0. So you can follow the pattern, right? This block is only contains information about the momentum. course, I need polarization vectors. So I'm going to mimic this structure here. Okay, so don't worry, the all this effort will pay off. Okay. Now comes the difficult part, the off-diagonal terms. As you can see, this matrix already looks antisymmetric, right? Remember these sigmas, when you flip the indices, they become minus each other, according to my definition. And then here, what I'm going to do is, if I see this is the column K, K1, I'm going to put K1 everywhere, except in this place. So I'm going to put K1 here, K1 here, all the way to K1 here. And I'm going to put a sigma that has an index 1 there. Okay? The reason I'm doing this is that the only way I can remember. So if I look here, this is the row epsilon 1 that depends on the epsilon 1. So I'm going to put an epsilon 1 here, 1 here, and epsilon 1 here, and sigma 1 here. Okay? Now when I go here, this is the epsilon 2. So I have epsilon 2, and here epsilon n, and I put the 2 and the n here. Okay? And I go on and on. So this is a K2 column. So I put 2, 2, and this is the m column, Km column. So I put the m, and I keep going. Now, this thing over here is whatever is needed to make the matrix antisymmetric. So we need, psi to be antisymmetric, okay? I haven't told you what these entries are. Okay? But these entries are nothing but minus the sum of the remaining guys in that particular row. Okay? Now I'm done. That's the object. Now what do I do with this? Well, I claim that to get gravity, any number of particles, all you have to do is to put here the determinant of that matrix. Or at least that's what you would think. This is something reasonable. Well, why is reasonable? First, you need something that is linear in polarization tensors. Right? Well, to make a polarization tensor, you can make a polarization tensor for a graviton by putting together two polarization vectors for a gluon. Okay? So whatever my amplitude is for gravitons must be multilinear in this one. So I need one pair per particle. No more, no less. Okay? Otherwise, this is completely wrong. So let's check that this determinant does the job. Well, if I rescale, say, epsilon 1 by a constant, just to see what the scaling is, what do I get? Well, epsilon 1 appears here, okay? And it appears here. So it appears in one column and one row. So when I rescale, the determinant picks up a factor, a power of the rescaling squared. So my object has precisely degree 2 in each polarization vector. That's good news. The next thing is that I have to check gauge invariance. Okay? So when you check gauge invariance, what do? When you have gravitons, if you replace any one of these two by the momentum of the particle, you should get 0, immediately 0. Does that happen? Well, look at here. Replace epsilon 1 by K1. Okay? And look at this row. At this row. First of all, this C11, if you put 1, 1, and you put a 1 here and a K1 here, that becomes one of these equations, so it vanishes. When this becomes K1, it becomes equal to this, so this row becomes identical to this row. So two rows become identical when I replace any polarization vector by the momentum. So you get 0 immediately. So you declare victory, and you say that this is it. Except that then you put it in Mathematica, and you compute the determinant, and you get 0. The determinant vanishes. So, why does it vanish? Say, I'm so close, how come? The thing does everything that I need, and yet it vanishes. Well, then you try 10,000 other things, until you realize that all you have to do is to put a prime again, and say that determinant prime of psi is equal to the determinant of a matrix that you get by removing 2 rows and 2 columns. And you divide by sigma ij squared. You put it in Mathematica several times and you check, and this object is independent of the choice of I and j. Okay? So just as before, this object is independent of the choice of I and j, and it gives you something that still has the properties that we mentioned earlier. Okay? Not only that, it has precisely the correct properties for this, together with this, to be SL2C invariant. So now the whole formula makes sense, and you run any other checks that people can think of, and the thing passes all the tests. So this thing is a formula that computes graviton, the scattering of gravitons at 3 level for any number of dimensions. Okay?
Before you go on, I'm a little confused about, spend out the Einstein-Hilbert action, look at indices for gravitons, arbitrary numbers. So you're including those data by accident. Are those all included or not?
Every single one of them.
Really?
Yes. Yeah. See, that's one. The point is that you know that those vertices are not arbitrary.
Yeah,
Right?
it's
They are all yes, that's right. That's the reason we know that there has to be something that, or that there could be something that put everything together in a single number.
But where's the coupling? Where's the strength of each vertex?
Well, you know, at 3 level, the coupling only enters as an overall factor, right? Sure, I could put G Newton to the correct power in front of each one of them, but I'm computing only single ones. I'm not putting them together. Okay? Very good. So we only have 5 more minutes to do everything else, right? But that's not very difficult because we all learned in kindergarten that if you have the determinant of an antisymmetric matrix, right, every time you compute it, you find something amusing. You find that it's a perfect square. You say, maybe I'll try now a 4 by 4. Oh, it's also perfect square. 6 by 6, it's also perfect square. Then somebody figured out how to prove it in general, and people gave a name to that thing. It's called a Fathi. So you say, well, fine. If this was for gravity, so this is my answer for gravity. How about this? Okay, so as we said, we have the determinant prime of this object defined to be 1 over sigma ij squared of the determinant of psi ij, which is a matrix obtained from psi by deleting the columns ij and the rows ij. So this matrix is still antisymmetric. And as I told you, any antisymmetric matrix, the determinant is the square of something called the Fathian of the matrix. Okay? Very good. But you probably have heard all over the place that there seems to be a connection between Young-Mills and gravity. People usually talk about Young-Mills, gravity as the square of Young-Mills. Say, well, I mean, if that's true, or if there is anything to that statement, then why not try to use this for Young-Mills, right? Then you do. So you write your formula for Young-Mills now for a spin 1. So that one was for spin 2. You have your integral over the sigmas with the volume of the cell to C, the scattering equations, and then you put your Pfaffian prime here. So it doesn't, it's very tempting to call this thing the Pfaffian prime because this was the Pfaffian after you remove the rows ij and ij, as well as ij. Okay? So I'm calling the Pfaffian prime this quantity inside. Okay? So you're very happy, you put it there, and you say, oh, I'm done, this is Young's. There is a problem though. First, there is no color. Gluons are supposed to have color structure. Second, this is not SL2C invariant. You needed 2 powers to make it SL2C invariant. So there seems to be a problem. What do we do? Okay? But it turns out that the answer to the problem is on the blackboard. Exactly. You're looking at the right thing. You put here C and you're done. That's C over there. This thing has the same SL2C variant, the SL2C properties as the Pfaffian prime. It's quite remarkable. This object here, it has a color structure. So all you have to do is to put it in here. Okay? So another one, check. Yes.
The fact that gravitational amplitude was symmetric, completely symmetric in all indices, and this one is not, is also hidden in C.
Sorry, what is it? C is permutation invariant in all the indices.
Okay, but the
amplitude of gluons is invariant in all the indices.
yeah, but the coefficients of different color terms on the guess.
Yeah, well, you can now study just the coefficient of a given color structure, and that would be this times the Pfaffian prime and all that. Yes.
But the Pfaffian is still fully invariant.
Yeah, the Pfaffian is fully.
Specific
Yeah.
only in the-
All the color dependence is here, just here. That's right. That's right. Now you say, well, this is great. You study this guy and you look. The more you study C, let me give a name to this one. Let's call it E. EM and CM. The more you study E and the more you study C, you realize that they behave more or less in the same way. And the fact that you can just replace one Pfaffian by C tells you that somehow they are exchangeable. Okay? But if that's the case, well, if the trick works once, why not twice, right? So let's do it again. Okay? So what if we now replace this Pfaffian again by another copy of this guy? What do I get? What theory do I get? So let's actually do it. It looks like a graviton. In the graviton I had E squared. In Yang-Mills I have E times C. And now I build another object that once again it makes sense. It's a SL2C invariant. It also has interesting factorizations. What theory could this be? Well, sir, it's a theory without polarization vectors or polarization tensors. And what is it? It's a theory with spin 0. It's a theory of scalar particles. What theory is it? I mean, that's a proposal, right? It could be nonsense. It could just be. Now, in order to tell you what the theory is, allow me to do something. In the Pfaffians, you see that the two Pfaffians that I had here, I had something squared, and this thing depends on some polarization vector, right? But nothing tells me that I cannot take one of these. Sorry. That I cannot take this thing, but I said E squared, and I'm going to replace this by something that depends on one kind of polarization vector, and the other one, I'm going to shift it by anything. I'm going to make a change of gauge. After all, each one of them by themselves are gauge invariant, right? That's why we work so hard. So I can choose this to be one polarization vector and this one another polarization vector. Nobody stops me from doing that. Okay? That's fine. So if I do that, nobody stops me here from doing something similar. These were the color structures of a UN gauge theory, of a UN color group. So I can replace the C squared by another C here with UN tilde. Another one. And this thing seems to make sense. Now when you work this out, you find that this reproduces the three-level S-matrix of the following theory. This is a cubic scalar theory. With interaction term of the form so this is a Lagrangian. That's a theory. Okay? Not only that, now following your observation, you could take these objects here and separate them by color structure, classify them by color structure. Okay? So you can now classify these objects, expand these sums that appear here completely and just pick a given color structure. So you get two powers or two factors of this thing. And when you put them together and you start playing with them, you find something remarkable. There is something truly remarkable, and it's that these individual factors that you get by expanding these two sums completely expand them out and just pick a single factor that contains one of these and the other one next to it. They have a very, very simple interpretation. So they are given by the sum of certain traveling graphs of a cubic scalar theory. So what there is, maybe 2 minutes, and I'll tell you what it is. Where should I do it? Yeah. Now you all remember by heart the metrics, right? So I don't have to do it there. So by expanding out those, you get terms that look like this. Integral ds sigma volume s to c, the product over these scattering equations, times 1 over that factor over there with some permutation. Let me call it the permutation alpha. Actually, I can put any permutation that I want, even from the beginning, alpha 1, alpha 2, all the way to alpha n. Times another factor that depends on another permutation that I can call beta. Now what this is equal to the following. Is equal to the sum over all trivalent graphs that you can embed on a plane such that the external particles fit nicely in a disk like this. And also, you can make them fit in a disk like this. Okay? Sum over all trivalent graphs that do this. Each trivalent graph is simply given by the corresponding propagators that appear in the graphs. So let me give you an example. If I have the permutation alpha to be 1, 2, 3, 4, and the permutation beta is the permutation 1, 2, 3, 4, right? Then clearly, I have the following diagrams. I have the diagram 1, 2, 3, 4, plus the diagram 1, 2, 3, 4, plus the diagram. Actually, that's it, right? These are the only two diagrams that I can have. What if I flip? What can I flip? Yeah. What if I flip 3 and 4? So if I flip 3 and 4, one, 2, 4, 3, then the only diagram that can be drawn on a plane consistent with both orderings is the first one. The second one doesn't contribute. So the answer will just be 1, 2, 3, 4. Okay? And what do I get explicitly? This is just 1 over k1 plus k2 squared, just the propagator. And here is 1 over k4 plus k1 squared. So these objects can nicely be evaluated in terms of these simple looking things. So it's quite amusing that to end the talk, we find something very spectacular, that somehow the scalar theory is actually the simplest one of all the theories we have.
You're such a jerk.
No,
No, but when you warned me yesterday, I didn't even think you would sink to such depths of depravity.
I promised you yesterday I was going to end the talk with a joke that only he could understand.
No, no, he did say that
Indeed, nobody else.
No, he did say, he started saying that the scalars are the hardest theories of all.
Oh, he started like that.
That was
Oh, sorry. Then I didn't know. Sorry, I mean it's a joke. It's I started with the graviton amplitude for a reason. Right?
but it's probably, physically, this cubic theory, probably as soon as you include loop corrections, it's probably going to generate masses.
This is a non-supersymmetric.
Well,
This
theory.
study this guy
This
six
is a non-
dimensions.
This is a non-supersymmetric theory, the scale.
Oh, it's conformal system.
This is in any dimensions. Choose your
It's
dimension.
not, probably not conformal.
Well, these at this point, these are creatures, right? But even if you're concerned about the existence of the theory, study it in 6 dimensions. Or the theory, this theory, this cubic theory says.
Yeah.
But yes, I mean, this is all at tree level. Now, of course, to end the talk, I should end with what's next, right? So what's next is that it's very tempting to say that this was all at tree level. So, and I was using a sphere. We all know very well that if you go to loops, then the natural thing to do is to add a handle to this. So is there a generalization? Of course, the generalization will have to depend very strongly on the kind of theories that you have. Because now you're going to see the whole spectrum running in the loop. Right? So now I cannot get away by saying I'm only studying external gravitons or only external numbers. Now I really have to know what the theory is. But the consistency of the theory will precisely tell me what is it that I do. Okay? So, yeah, maybe I should have stopped.
The questions for Freddy.
Just to make sure I understand, so if you want MHB and H theory, right, then CN
Sorry,
is
if I
the
want
answer.
what?
If you want an MHB answer, right, then CN is the answer.
I mean, you're thinking so four-dimensional. There are no MHB amplitudes in 6 dimensions.
Yeah. But
you insist in 4 dimensions.
yeah, I just wanted to see how it works in the simplest possible case, right?
Now-
And
now-
CN is the answer, so
Yeah, now-
sometimes it has to be one.
Now that you insist that it's not my fault, it's his fault. Yeah, so we started the whole thing with this map, P mu this set of polynomials, right? If you're in 4 dimensions, if you should be in 4 dimensions for any strange reason, you know that you can contract this with the power metrics and make a matrix of polynomials. So this is a matrix of polynomials. Whose determinant has to be 0. Okay? So the determinant vanishing implies us that P11 dot as a polynomial times P22 dot has to be equal to P12 dot times P21 dot. Okay? Very good. But now, these are polynomials, right? And I told you that this was a polynomial of degree n-2, and so is this one, so is this one, and this one. But this equality of polynomials tells me that any root of this guy has to be a root either of this guy or of this guy. Okay? So I have to start making choices. So let me denote the first, all the roots of this guy that belong to this guy, I'm going to put them here. And I'm going to call them ZA, from 1 to some number m. Okay? Those are the ones that appear here. Okay? The rest must go here. Okay? So let me call the remaining ones B. Okay? Sum over B. Up to n minus 2 minus m, of course. And these guys will go there. And the same thing happens with this. So this is telling you that the solution set of this problem falls into classes labeled by an integer. Okay? And clearly, well, if this guy is going to be, well, so if I keep doing that, I can complete the whole picture. And what I find is that this polynomial that enters here, maybe I should give it a name, and I'm going to call it lambda 1 z. It's nice because the 1 appears here and the label 1 appears here. And this polynomial that appears here and appears here, there is a 1 dot, so maybe I should call it lambda 1 tilde dot of z and put it here. Okay? And the same thing for lambda 2 of z and lambda 2 tilde z. So just from this consideration, we see that in 4 dimensions, the whole amplitude splits into sectors. So it's already telling us that there are sectors, and the sectors are classified by an integer. And the integer defines maps of different degrees. Now you should remember how I started the talk. We can define an object that maps CT1s into twistor space, but if you completely remove twistor space and you just go straight to momentum space, you will find these little maps with degrees that depend on the number of negative helicity particles, or the MHP sector. So just from this little exercise, you discover helicity in 4 dimensions as a consequence of imposing that this map is a null vector. So to answer your question, you now take the solutions of these equations that correspond to the sector where this polynomial has degree 1. That would be the MHP amplitude. And MHP, take this guy to have degree 2, and so on.
But then somehow if it's MHP, you will get Cn out of your formula after you do all the integrals. Because that's
well, but if it's of degree 1, everything localizes. The sigmas become the lambdas, and I get the per Taylor answer in the square. Yes. So here is a challenge for all of you. I don't know what the analog of this equation means in 6 dimensions. There is a similar equation to this, but now it has 3 terms, and I don't know what it means. So it would be really nice to understand what it is. Okay, now.
So what's the relation between what we heard from you and what we heard?
That's the next question for you guys. No.
I mean, is that very guesses?
Well, we know in 4 dimensions that these formulas like this can be connected to residue theorems to formulas, to the Grassmannian formulas. So you could try and see if in higher dimensions you can play the same game and discover other formulas.
And it's also true that BCFW Persian relations work in higher dimensions.
That's right.
They do in 4 dimensions. So there are, and that has been hardly developed at all. I mean, hardly anyone's written the explicit formulas that even it's straightforward, but hardly anyone has done it. But there's a beautiful set of BCFW formulas which are, again, blocky. They're the blocky formulas. And they should somehow be related to these, they must be related to these smooth formulas somehow.
Right. And very likely they are related. In this, what we have learned in the last few years is that any 2 things that must be the same, they end up being the same due to a global residue theorem. And if you don't know what global means in this context, then you should read chapter 6 of 3 design habits.
No, you should not read chapter 6 of
No, you should read Wikipedia. It's very well explained there. No, but just the higher dimensional realization of the standard residue theorem. So there is a residue theorem for more values.
I mean, it's as Freddy was just saying too, it's, we're sort of cycling back to the beginning of the story. So, you know, you start from add twistor strings, and then, you know, it goes off in that direction. It's a smooth, blocky develops some more, still nothing for gravity. Now, smooth is backward of vengeance with gravity. Everything. So somehow, you know, the entire, all the stories have to develop in parallel somehow. And it's not. Yeah, there's a lot of words.
Yeah, it's fine.
Is there any more questions? Okay, so let's thank Freddy and Nina.